Dr. R. Sugurat Samuel is working as professor in physics in SRM University, Chennai. He is also training students for IIT JEE, AIEEE and BITSAT. He has more than 16 years of academic experience both in teaching and research. He has published a book titled The Complete Handbook of Bachelor of Electronic Science Practicals. It is prescribed book in the syllabus for BSc Electronic Science by University of Madras. He has attended and presented papers in several national and international conferences and conducted many training programs and workshops. He has experience in both regular classroom teaching and also online teaching. His research areas are ultrasonics, polymers, crystal growth, and photovoltaic systems.
Welcome to UGC lecture series on Applied Sciences Electronics. We have been listening to a series of lectures on the subject Electricity and Basic Electronics, which is the first paper in the first semester of the program. This is the 36th lecture in the series. In this lecture, we are going to see an important application of diode. In the last few lectures, we have been listening to the applications, and one such application today we are going to see. Let us see today's session outline. In this session, we are going to see the recall of diode operations, clamping circuits, positive and negative clamping, clamping without and with threshold. We started off with the semiconductor device diode several lectures before, and after that one by one we are looking at lots of applications of the diode. We saw the special diode as Zener diode and how a Zener diode is used in a power supply. The entire concept we have learnt, and then how a diode could be used for the clipping operation for removal of certain portions of the input wave or the input signal, how diode could be used in the forward and reverse bias conditions. Elaborately, we have discussed about the clipping circuits in the previous lecture. And in today's lecture, another such application of the diode we are going to see, that is a clamping circuit. For this also a diode is used. First, let us see what is the clamping operation. Technically, what the word clamping means. Let us see what does that mean. Before we do, let us recall the diode operation once again. This we have been doing invariably for all the applications of diode. A diode in the forward condition, forward bias, is acting as a switch which is closed, or it is said as turning on of the diode. The diode conducts current, so it does not, an ideal diode does not offer any resistance, so the entire current flows through the diode. And in the reverse bias condition, when the positive of the voltage is applied to the N region of the diode and the negative to the P region, it is reversely connected. So, it acts as a open circuit. The current is not flowing through the diode. The diode offers infinite resistance. If it is an ideal diode, it will not allow the current to flow because it offers a huge resistance, which is nothing but an open circuited connection. The connection is broken. So, these are the two operations of a diode. In the forward bias it conducts, and in the reverse bias it does not conduct, which is like the on and off of a switch or closed and open of a electrical circuit. With the property of this diode, how the clamping operation is done. Let us see what the clamping operation refers to. Clamping operation. Clamper circuits, or briefly clampers, are used to change the DC level of a signal to a desired value. Basically, clamping is a shifting operation. The signal is just shifted either one side of the zero reference level, and there is no change made to the original form of the signal. So, in one word, when we want to say what the clamping refers to is shifting. It is just shifting it on either side, either on the positive side of the reference 0 or to the negative side of the reference 0, without altering the waveform. The typical variation of the signal should not be altered, but only the shifting should be done. When we explain like that, we are not able to visualize what the shifting means, but when we look at a shifted wave, we will be able to get a complete idea of this clamping operation. So, let us have a look at the diagram and try to understand what this shifting means or what the clamping operation means. Based on the shifting of the input signal, clamping operation can be classified as positive and negative clamping. In positive clamping, the shifting is to the positive side of the signal, and in negative clamping, the shifting is to the negative side of the signal. This is how we classify the shifting phenomenon. On either side, we can shift the input wave on positive side or on to the negative side. Let us see how the positive shifted and negative shifted or positive clamped and negative clamped operations produce the output wave. Let us have a look at the diagram. So, this picture gives us an idea of how a clamped signal looks like. This is the input wave, and if it is said as a positive clamper, the reference here in the input is 0, but in the positive clamped signal, the reference is a positive DC value. So, with respect to this, the oscillation is continuing, or the variation in the signal, the voltage variation in the signal is happening. The same way, in the negative clamper, the shifting is done to the negative side of the reference 0. So, that is why it is called negative clamper. But when we look at the waveform, as such the waveform is not altered. Note, the shifting is done to the positive or negative side of the input signal without changing the original waveform. The waveform is not altered either in the amplitude or in the frequency or time period. The waveform is not at all altered, only the shifting is done vertically either on the positive side or to the negative side. It is more or less adding a DC value to the input signal. When you just add a DC as a positive value or a negative value, then this kind of clamping is achieved. But how do we achieve this with the help of a diode? Simply adding a DC value could be done using a battery eliminator or a voltage source, but here we are looking at the applications of diode. So, how a diode is used for the clamping operation? We need to look at the property of the diode and try to understand how the clamping is possible with the help of a diode. In the earlier lecture, I have mentioned for the clipping operation, we use a resistance. We have used a resistance and a diode connected in the forward or reverse biased condition, we could get the clipping operation that we have seen. But in the clamping, we need to have the charging discharging property of a capacitor. That point I have already mentioned. So, here we are going to use a capacitor for the charging discharging of values, so that the clamping operation is performed. Being different from clippers, clamping circuits use a capacitor and a diode connection. When diode is in its on state, the output voltage equals to diode drop voltage, ideally 0, plus the voltage source if any. Now, let us examine the clamping process for the circuit. As we know, this circuit in fact is a series RC circuit. The resistance of diode several ohms above its drop voltage and the small capacitance yield to a small time constant for the circuit. And here this is a clamping process. We just for reference have taken a digital input wave, so that the forward and reverse bias condition would remain stationary or static for a particular time, and this is how the clamping is done. It has a capacitor in series and a diode connected in this manner, and the output voltage is taken across the diode. If we want, we can have a load resistance across the diode and take the output as E naught here. How the clamping is done? Let us try to understand. When the positive signal is there in the capacitor side, the current flows in this manner. The diode is forward biased during the positive cycle, which is connected to the capacitor terminal. This means that the capacitor will rapidly be charged if any input voltage is given, that is enough to switch on the diode is applied. The diode will conduct during the positive cycle of the input signal, and the output voltage will be ideally 0. In practice, this voltage equals to 0.6 volt. At this point, we need to mention, when the diode conducts current, there will be a gap, there will be a potential drop across the diode. That potential drop will be very less, because the diode is conducting the current, so it will not offer much resistance. So, ideally the voltage would be some 0.6 volt, it is very less, comparatively very less. When we say comparatively, it is compared with the input voltage. The diode conducts during positive off cycle. So, the transient condition is taken, it is positive, this terminal is positive, and the diode is in the on condition. So, there is a closed circuit, there is a connection made here and the current flows. So, at that particular instant, this end will be negative. Note that during positive cycle, the capacitor is charged rapidly in inverse polarity with the input voltage. The inverse polarity is shown here. When this end is positive, the capacitor also, that particular end of the capacitor is positive and the other end is negative, and when we take the closed circuit, the loop, when we take, at that time it seemed to be a reverse polarity for the regular circuit potential drops are concerned. So, it is said as a reverse polarity condition when the capacitor is charged, and at that reverse polarity charged condition, what will happen when we consider the loop theorem? We are familiar with the loop theorem. So, when we apply the loop theorem, we will be able to find out the output voltage in terms of the input voltage and the voltage drop that has happened across the capacitor. We shall take the loop theorem applied to this circuit after a short break. Welcome back. We have to apply the loop theorem or the voltage theorem for the closed loop that we consider here with the input and the voltage drop across the capacitor and the voltage drop across the diode. But before we do that, we will have to consider what will happen when the negative cycle comes, when the capacitor is fully charged with the reverse polarity. The negative pulse when it comes, when negative cycle of the input signal when it reaches, when it is happening, at that instant what happens? Let us have a look at the diagram once again. After transition to negative cycle, the diode becomes to its off state. In this case, the output voltage equals to the sum of the input voltage and the voltage across the terminals of the capacitor, which have the same polarity with each other right now. And this is the case when the negative cycle is appearing across the two terminals of the input with the negative potential appearing at the point where at the terminal where the capacitor is connected. At that instant, the capacitor is having the same polarity still. This part is positive, this part is negative. So, during that instant of time when we write the diode is in the reverse bias condition, we know in the reverse bias condition the diode will not allow the current to flow through the diode. So, it will offer a very huge resistance or say ideally infinite resistance. So, there is a voltage dropped across the two terminals of the diode, and when we write the loop theorem here, EI is one potential drop and EC is another potential drop and E naught is the other potential drop. So, when we write them, we get an equation like this. The output voltage E naught is the negative of the summation of these two instantaneous potential EI and EC. Here EC is the potential drop across the capacitor. So, what has happened here? The output voltage E naught is now the summation of the voltage of the input and the voltage that is dropped across the capacitor because of the charging phenomenon happened during the positive cycle. So, the output is now negative and it is a summation of the two potentials. So, it is shifted. Now, the reference is shifted downwards. So, what is the output of the clamped signal here? Let us have a look at the clamped signal. The resulting signal after a complete cycle is shown below. So, it is totally shifted downwards and this positive part is now coinciding with the 0 level here. So, the variation is happening keeping the negative value as the reference. Because we have taken a digital signal here, we should not misunderstand that the positive or negative part is removed. It is not happening here, but it is shifted. So, the oscillation is happening with respect to a negative voltage here in this case. So, this is the operation of a negative clamper. So, we know how the diode is conducting current during the positive off cycle and the capacitor gets charged. After that, during the negative cycle of the input voltage, there is a potential drop still dropped across the capacitor and that gives a shifted voltage at the output. And when we choose the value of the capacitor here, it is actually an RC circuit. Where is the resistance here? And in this case, the resistance could be taken as the resistance that is dropped across the diode or the resistance offered by the diode. That is a correct way of telling it. So, during the forward biasing of the diode will offer a small resistance. So, that resistance is there in the circuit. We should not think that there is no resistance in the circuit. During the positive cycle, when the forward bias is done for the diode, it offers a small resistance, maybe a 0.2 or 0.6 ohm. So, that is acting as a resistance in the circuit. So, it is a RC combination, and because of that the charging happens, and after that the instantaneous voltage is taken as a negative value when the negative circle appears across the input part, and thus the voltage is clamped, it is shifted. Why here the RC values are very small? Because the quick discharging should happen. In the case of the smoothing of ripples, we studied that, and in the topic construction of regulated power supply, there also we use the charging discharging property of a capacitor for smoothing the ripples, for removing the ripples. At that time we had a very huge value of the time constant. RC value was supposed to be a large value, so that the time constant is large. So, the smoothing, the charging is very high, the charging time is fast and the discharging time is very much delayed, thus the voltage remains constant. So, that concept has been used, but in this case as the input is varying quickly depending on the frequency, the discharging should also happen quickly, so that the waveform is not altered. So, here the RC value will be very less. So, let us see how the RC value is chosen. By this process, the input signal is shifted to negative DC value. Its maximum value is ideally 0 without any change in its amplitude ideally. There exists again a modified version of this circuit in which a threshold value is inserted for clamping. We have considered in the clamping operation the reference level originally for the input was taken as 0. After that the shifting was done by the charging discharging property of the RC network that is there in the circuit. Then for the positive clamping, what is to be done? For the positive clamping, we have taken the negative clamping for our discussion. How the circuit is to be modified for the positive clamping? The only thing to be done is the diode has to be just reversed in polarity. Once the diode is reversed, the operations are performed in the reverse manner. Now, the voltage, output voltage will be the summation of the voltage of the input and the voltage that is dropped across the capacitor, but now the value will be positive. So, the total value seem to be a shifted value towards the positive side of the reference 0. So, like that we will be able to have the shifting done either to the positive side or to the negative side. Now, the question arises in our mind, is it possible to shift this by a desired reference value or a desired threshold value with the same circuitry without altering anything? With the same circuitry, is it possible to fix our own threshold? So, that is also possible with the help of the added potential sources or the voltage sources. Let us see how the addition of the desired DC value is done with the help of potential sources. Let us have a look at the diagrams, and there will not be much explanation in the case. The diagram itself is self-explanatory. Let us have a look at the diagram. There is a EMF source attached. It is connected in series with the diode. So, this is how we have discussed the case. It was a negative clamping. So, when the diode is connected in this manner, it is a negative clamping. So, shifting will happen with respect to the reference 0, but downwards. So, it has happened here. Because of this E which is connected in this manner, it is not shifted completely, it is shifted to some extent, keeping the E naught here, because it is already present in the output terminal. So, with respect to this E only, the shifting is done. So, it is not fully shifted downwards, and once again the shifting is done totally, but now too much to the negative side, because here the potential source is connected in the opposite manner, and because of this minus E is there. So, that becomes the reference here. Actually, the reference is this dotted line. So, with respect to that, the signal is varying on either side of the reference, but the E naught decides the shifting part. So, if we want, we can take the E naught, the negative E value plus half of the amplitude as the reference. So, shifting is done with the threshold values with the help of the connected power supplies in series with the diode. Because we have taken up a negative clamped circuits here, we have not taken the diode in the other type of connection or the reverse connection. If we do so, we will definitely be able to get the positive clamped signals. The signal will get shifted to the positive side of the input wave. So, I have not shown the graphical, I have not given the graphical or the diagrammatic representation for the circuits. It is up to us just to consider the diode in the reverse biased condition. In the opposite connection, we have to use it. So, we have got a picture of how a clamping circuit works. The clamping circuits are shifting the input signal either to the positive side or to the negative side of the input signal. So, with this, we have seen lots of applications of diode. In rectification, diodes are used, and in voltage regulation, diodes are used, and in clippers for removing the part of an input signal, diodes are used, and for clamping also diodes are used. There are lots of special diodes also, like the light emitting diode, photodiode. So, they are all coming under the subject optoelectronic devices. We have lots and lots of applications of diode in the field of optoelectronics, but those topics are beyond the scope. So, we are not going to discuss about those types of special diodes here. We have just seen the applications of some of the diodes. In the coming lectures, we will be able to take up the other electronic device, namely a transistor. So, with this lecture, the concept of diode gets over. Let us see today's session summary. In this session, we have seen the recall of diode operations, clamping circuits, positive and negative clamping, clamping without and with threshold. Let us test our understanding by answering these questions. What is the property of a diode that makes it suitable for clamping operations? Explain with diagrams the positive and negative clamping operations. Explain the role of capacitor in the clamping circuits. Draw a clamping with threshold and explain its operation with the output waveforms. So, with this, I would like to conclude this lecture. Hope to see in the coming lectures with the concepts of transistors. Until then, goodbye. Thank you.